Hello. We're going to get to the last bit of Chapter 8 that we are covering here. There's my laser pointer. Um, Estimating population proportions. Um, so this is the actual, 4 out of 5 dentists prefer Trident or Crest or all of those 4 out of 5 um, taking the sample and coming up with what they think American voters think, for example. So population proportion is, again, just a lowercase p. It's the fraction or percentage of a population that displays a certain characteristic. So, 36% of Americans approve or disapprove or whatever of the president. That type of statistic. Um, when a sample's large, like the population of the U.S. or even the voting population of Marietta or Athens, it's pretty much impractical or impossible to find the actual population proportion for that. So we have to go with the sample and use that sample information then to infer what's going on with the overall population. The sample proportion is, p with this little hat over it, so p hat. It's the fractional part of the sample that displays that characteristic. It's usually the best estimate for estimating what the population proportion is. So, for example, if we have a graduate student who wants to know the proportion of American adults who are at least bilingual, and he randomly surveys 565 randomly selected American adults and finds that 226 speak at least 2 languages, what would his estimate of um, all American adults who speak 2 or more languages be? Okay, so again, we're going to use p hat as the best estimate we can come up with for p. Right? P hat is the proportion of the amount of the population that fits our criteria we're after, or sorry, the amount of the sample, and lowercase n is our sample size. So in this case, it's 226 American adults who are at least bilingual and 565 total sampled for 0.04, 0.4, or 40%. Honestly, that seems like it's probably a little high. I would not expect that 40% of American adults do speak at least 2 languages. Okay, so given that, what we need to come up with is a confidence interval. What we need is a confidence interval that tells us how likely the real answer is to be close to that. Um, so as we did in the previous sections, we make use of the central limit theorem, and there's a few criteria that have to be met for that to work. First off, and as we saw previously, we have to have a simple random sample. We also need to meet the conditions for a binomial distribution for this, and we have to have a sample size that's large enough that our sample size times the sample proportion is greater than 5, and the sample size times 1 minus the population proportion is greater than 5. If these are met, we can apply the central limit theorem and make a confidence interval just like we did for estimating the population mean. Okay. All right. We use this formula here. So we're back to using the standard normal distribution table and not the t-tables with this. So it's z sub alpha over 2. So our critical z-score here. Just as a reminder, that is the alpha represents the likelihood that we're outside of the range we're after. So let me just sketch this here. If we have our simple normal distribution, standard normal distribution, and okay, hold that up here. So we've got C is our confidence level we want. Again, 95% is a fairly standard portion for that. Alpha over 2 is what's outside of that on either tail. So remember, 1 minus C equals alpha, right? And Z sub alpha over 2 and negative Z sub alpha over 2 are just the Z scores that correlate to that boundary in between the confidence interval, the area we want our confidence to be in. I'm phrasing that very poorly, I'm sorry. It's just that boundary between where we think it is and what we're not so confident about. All right. Again, Z sub alpha over 2 is the critical Z score for our level of confidence, which is C. C equals 1 minus alpha, or alpha equals 1 minus C, either way. The area under the standard normal distribution to the right of Z sub alpha over 2 is equal to alpha over 2. Again, we can just use the critical Z scores from table 8.2. So if we want a 95% confidence level, C is 0.95. Alpha, or 1 minus C, is 0.05. Alpha over 2 then would be 0.025. The Z score associated with that is 1.96. As before, the confidence interval is just our sample proportion minus the margin of error and our sample proportion plus the margin of error. E is that estimate for margin of error that came from this equation right here. Okay. So, again, for example, if we survey 345 random students at one university and finds that 301 of those 345 think that there's not enough parking. So we want to find the 90% confidence interval for the proportion of all students who think that there's not enough parking on campus. First step is to find our point estimate, which is going to be our sample proportion. So that will be 301 over 345, or 0.872464. All right, we want a 90% confidence interval. So we want to find the margin of error. So we look up the Z sub alpha over 2. Easiest way to do this is to go back to this table. We want 90%. We have 1.645 there. 1.645, and then we can use that formula. I'm not going to flip all the way back to it. Use this formula. Z sub alpha over margin of error is Z sub alpha over 2 times square root of proportion times 1 minus the proportion over the sample size. So we've got the 1.645. The sample proportion was 0.872464. multiply that times 1 minus 0.872464, divided by our sample size, and we get 0.029542. Sorry. Add and subtract that margin of error from the point estimate, and we get, all right, so we subtract it, we end up with about 0.843. We add it, we get about 0.902. So we can write it either with an inequality or as an interval form. Either way is fine. And basically we're saying we're 90% confident that between 84.3% and 90.2% of all students at the university think there's not enough parking on campus. We could do this with the built-in functions in the calculator. We actually need to do a little bit less work because some of it we can do automatically with the calculator. So really, for this, we just need the sample size, the number of members of the sample that have the characteristic we're interested in, and the confidence level. Okay, so doing this on the calculator, we have a study where they surveyed 820 American adults, and 61% said they would travel less this year for non-business trips than last year. We want the 95% confidence interval for the true proportion of adults who said they would travel less this year for non-business trips. In this case, we are going to have to calculate that x, the x being the number of surveyed adults who said they would travel less. Right, we need those three pieces. We need N, which is 820 American adults, X, which is whatever 61% of 820 is, and the level of confidence, which is at 95%. So in this case, we need to find X first, as I said. Since p hat is equivalent to that fraction, p hat is 61%, it's going to be x over n. We can rearrange that equation to get x equals p times n. So 0.61 times 820, we get 500.2. We can't have a partial adult, so we can round this to the nearest whole number. So we've got 500 adults have the characteristic of interest. So clearly there's some rounding error here. They've rounded up or rounded down to 61, probably rounded up slightly. And this should, this is probably 60.9 something or 8 something to get to actual. So we've got an x of 500 now. We can go in and go to the statistics menu, select tests, and tell it we want to do proportion z int. I'm not sure what int stands for, so prop would be proportion. We want it to use a z-score. Int, I'm going to guess that's going to be interior, so I'm guessing that it's interior, and something about exterior or tails would be the other options. That's just a guess though. So we go into that menu, we can put in the C level, confidence level, sample size, number of responses that have the criteria we're after, tell it to calculate, and it will give us will spit out that proportion for us and spit out the confidence interval in interval notation. It spits it out in interval notation. We can still write it as an inequality also. And we're 95% confident that the true proportion of Americans who say they will travel less this year for non-business trips is between 57.6% and 64.3%. Again, the other thing that this is one of the other things this is useful for is estimating what the minimum sample size we need is to find this population proportion, because as you can imagine, sending out samples so that you surveys so that you get a good number is expensive. You got to mail the survey out or make the phone calls or whatever. And then inputting all that data and analyzing it is expensive too. So a good question is, again, how many do we need? So again, we can take the formula for margin of error and rearrange it to solve for n, and we get a formula that gives us our minimum sample size for estimating a proportion. So in this case, n would be our minimum sample size if we've given some margin of error we want it to be within. Everything else is the same. We've got our population proportion. So we do need to start this with an estimate of what the population proportion might be. So given an estimate of the population proportion and the desired margin of error and confidence level, we can figure out what the minimum sample size is for that. That estimate of the population proportion is basically your hypothesis. What do you think it is? Those have changed. So as I said, typically the value for population proportion is an estimate or perhaps a value, sample value from a previous study or a similar study. If we don't have one we know, we can still use the formula for our desired level of confidence and maximum margin of error, and maybe use our best guess for population proportion. For example, if we estimated at 0.5, we'll find a sample that's large enough to give us the confidence interval regardless of the actual value of p. In this case, you always round up to the next larger whole number. You can't have a partial data value. I can't. Partial data points don't exist. And again, this is just a minimum. It's always a good idea to have more. All right, so what's the minimum sample size needed for a 99% confidence interval for the population proportion if the previous study of 820 adults and their travel, predicted travel patterns, if previous, oh, sorry, I misread that. Not the study from the previous example. So a previous study on something similar had a estimated population proportion of 0.54. We're doing a similar study. We want a 99% confidence interval and a no more than 2% margin of error. Okay, so we've got this 2% margin of error here. 0.54 is our proportion. So, all right, we've got 2.54. Margin of error to be at most 2%. We'll convert that to a decimal as 0.02. So it's 0.54 plus or minus 0.02 is what we're kind of initially estimating. We can look up the critical z-score with the value of 0.99 and we get 2.575. So now we've got all the data points we need. There's our 0.54, our population proportion from the previous study. 2.575, that's our critical z-score, and 0.02, that's our 2% margin of error that we want. So for that we need 4,118 samples. Again, we can also do this with the TI-8384. Going to use the inverse normal function under the distribution menu. I'll let you look at the syntax for that as you want to. Look up inverse normal for 0.995, and that will spit out the critical z-score associated with 0.995. If we use that z-score value with the same equation, we get 4121. Previous answer was 4118, so it's very close. So we've got 3 digits after the decimal here, and quite a few more here. And really, that I would have expected that to round up. 575, is this 57? No. I would have thought the table would have rounded up there to 576, but it doesn't. Interesting. And that's where the difference comes from, is that rounding error. All right, another example. If our state education commission wants to estimate the proportion of 10th grade students in the state who read at or below the 8th grade level, their initial guess is that it's around 21%. They're probably basing this on test scores and whatnot, maybe some trends they've seen, but they've got a guess that it's 21%. First thing they want to know is how large a sample would be required to estimate the proportion of all 10th graders in the state. With an 85% confidence level and error of at most 0.03. So we're looking for a 3% margin of error, 85% confidence level. Next part of the question. After they've chosen their minimum sample size, they find that 84 read at or below the 8th grade level. Using that information, find the sample proportion based on that. So, part A, calculate the minimum sample size. Part B, use that minimum sample size you just calculated to find the sample proportion with 84 meeting our criteria. Part C is construct the 85% confidence interval for the population proportion that you calculated in Part B. I'll go ahead and give a second. Go ahead and pause it, try to work through it, unpause it when you're ready to proceed. Okay, we know that we've got a 3% margin of error and a 21% estimated population proportion. We can use the table of critical z-values, which was earlier in the presentation, or table 8.2. It's actually given in a few places in chapter 8. Come up with 1.44. We calculate our minimum sample size with those. So there's our estimated population proportion, our 0.21. Our critical z-score, 1.44. And our margin of error is down here, 0.03. So we've got 382.2366. Since we can't have a partial student sampled, we'll round up to 383. If we use the TI-8384, we'll end up with 382 when rounded up, because Again, with rounding error, got 1.44 there and 1.439531 here. So it's a small difference due to the rounding error. Okay. All right. So our sample size is now 383. So to find our proportion, we'll divide the number that met our criteria by the sample size. We'll get 84 divided by 383, which gives us 0.219321. So their estimate was actually pretty close. If we use the calculator, we get 0.219895. So still very close, 2193, 2198. So again, using the confidence interval to find the margin of error, and we wanted 0.03. Let's calculate the margin of error. We'll put in our critical z-score, our actual sample proportion instead of the estimated one, and our sample size, and we get 0.030447. So very close to what we wanted, maybe slightly over, but very close. And we can add and subtract that from our sample proportion to get our confidence interval, and that comes to 0.189 to 0.250, and just subtracting our margin of error from the sample proportion and adding our margin of error to the sample proportion. So we'd be 85% confident that the actual population proportion is likely to be in that range. And again, we can write that either as an inequality or with interval notation as such. And using the calculator, we get the same values. Okay, and that is it.